Hey there, and welcome to the next part of the easy speedrun. So we have another 10 problems today, and most of them are going to be linked list problems with some trees. So let's get started. First, we have the famous reverse linked list, which is in all the memes where people can't get a job because they can't reverse a linked list, so hopefully you can do that. It's pretty straightforward. So current. Oops. Oh man. Previous, then prev equals cur. Temp. There. Temp. And then okay, and then we just return previous, I think. Hopefully that'll do it. Yeah. Okay. Merge two sorted lists. Pretty straightforward. I have a problem on merge three sorted lists, so we just make a dummy node, and then so close list node. We just do this, and then we say, well, there's something in each list, so list one and list two. Yeah. So then if list one is less than list two, and this is val. So we just compare values and take the smaller one until one of them isn't there, and then we just add whatever remainder is if there's anything left. So if this is this, next equals list one equals list one dot next, dummy equals dummy dot next. Otherwise, we do the same thing for the other side, right? So 2 next. Then we simply do this again, and there should be some empty. One of these should be non-empty usually, so list one, we don't need to have this check. Okay, and same thing for while list two, right? So you can definitely make this code cleaner, but to make it fast. Okay. Ooh. Oh, right, we never returned, so. And we also, yeah, so. We actually screwed one thing up here, so this cur needs to be done. We need to have a current node. So this actually needs to be that, and then that. Okay. Yeah. That should be fine. Okay. Palindrome link list. Okay. So let's just do this the fast way, I guess, and then we can talk about the follow-up in the future. So the fast way is simply we just have some kind of output, right? So something like res equals this, and while head res.pend head.val. Then we have a left and a right pointer to double check if they're the same. Actually, we can even make it simpler, so we can even do this. Don't even need these pointers. We'll just do it really fast. So res plus equals head.val, and then we can str this. This isn't the most efficient, but we'll talk about the most efficient method later, and then return res equals res reverse. Should work. What do we got? Okay, maybe. Okay. Actually, let's do this instead. So let's actually do head.val. Sure. Yeah, I don't think you can do that syntax with a string, so we can even do this. Okay. Interesting. Okay, let's just do a left and a right pointer. I'm not sure why that's not working. That's kind of funny. Oh, I see. I never did, there we go. That should work, right? No. Oh, okay. Okay, so I'm just missing everything. Okay, there we go. Alright. Removed linked list. So we want to remove all the nodes that has val equal to val and return the case. So we're going to make a dummy node again. Equals node 0, and we'll just say next is head. So then cur, same thing, equals dummy, and then we're going to do while cur. Do we want to do while cur? I think we want to do cur equals head, actually. Yeah. So if cur.val equals val, then we just move on. Otherwise, we want to append it, so we need another, yeah, so we need cur2 maybe. Yeah. Okay, there we go. So else we need to append the node that we're currently at. We could have technically actually, yeah, let's just do this instead. So instead, let's just do while head. Okay, that'd be easier. So we're just going down the list and we're taking, so this else is going to be the values we need. Okay. And that's going to be cur.next equals head. And then we have, yeah, we have head equals head.next. We return dummy.next here. Well, I might have missed one more line, but let's just see this. Yeah, definitely did. Okay, so if head.val, that's fine. Cur.next. So let's just see what this looks like. It would add it. Head equals, oh, we forgot one more thing. So let's see if, I think this is the least amount of code, but we might need one more thing. Yeah. Okay, so cur.next equals head. Head equals head.next. I think we also need to do a cur.next equals none is the other thing we need. We can do that at the end. I think that should do it. Okay, what did I do wrong? So it's head, so how are we outputting this? That's interesting. If head.val equals val, head equals head.next. Okay. Else. So technically we should never be, oh, I see the problem. So we have this should not be, this should be none. There we go. Okay. Given the head, delete all duplicates, which is turn the linked list sorted as well. Okay, so in order to delete all duplicates, what we need to do is we need to have a visited, we need to have, yeah, visited set, so. And we can do the dummy, same thing. And we can just keep adding to it. So actually, I think we can just copy this node, honestly. Okay. So cur equals dummy, while head. And then now this will just be in visited. There we go. Then, okay, hopefully that's everything I need there. Let's see. Oh, right. Cool. Okay, middle of a linked list. Alright, so there's two cases for middle of a linked list. There's either a fast or a slow pointer. And so I think the way, or there's either an even or an odd. So I think you want to have a slow and a fast here. You want to have the fast go by 2. So let me see what that would look like. 1, 2, that would go 2. And then here would go 1, 2. if there's two middle nodes, I want to return the second one. So what if I start, yeah, let's see, 1, 2, let's go 1, 2. Okay, so the problem is it would work for this, but it wouldn't work for this, right? So 1, 2, yeah, okay, 2. What if I instead just say, so I think I know how to make this work for this actually. I would just say if the fast would go here, here, would just say if fast dot next. Then it would go one more, right? So one more. Yeah, okay. So, and I'll explain it after. So slow, fast equals head, head. Now I need to do while fast dot next. Slow equals slow dot next, fast dot next dot next. And we should return slow, and that should work. Another way to do it would be to just get a count, go through it one at a time. Is it not next? None type. Oh, right. Wait. I see. I see, yeah. So, fast. And I think that should do it. Let's see. Yeah. Cool. Okay. So linked list cycle. Okay. So return if it's a cycle. Okay, so it's going to be pretty straightforward. I think every number is positive. So what we're going to do is do the tortoise and the hare. So with a slow and a fast. Yeah, so slow, same thing. Fast equals head, head. And are there unique values? Position equals -1. They're not necessarily unique. Okay, so while fast and fast.next. So if, or we need to move them up one time. So let's do that. So slow equals slow.next, fast equals fast.next. And there we go. So if slow equals fast, return true, return false. Okay. So intersection of two linked lists, kind of similar, except now we're just going to turn every node into a negative, because I believe all these nodes are positive. Yep. So we're going to traverse list A, make every node negative, then traverse list B, and if we run into a negative node, we have an intersection, and then we're going to traverse list A again. I think they want, yeah, so we're going to traverse list A again to make them all positive. So cur equals head A, cur times equals -1, cur equals cur. Next. Okay, there we go. Now we do the same thing for, and then we have some kind of output variable. So res equals false. And then if there's an intersection, so cur, now we make it head B. And while cur, same thing. If cur.val is less than 0, then we do res equals true. Return the node at which they intersect, actually. Okay, otherwise return null, so we can return none. Res equals cur. And then we can break here. Okay, and then we do this thing again and we make them all positive. So cur equals head A, while cur equals, so this actually should be cur.val, and this is going to be cur.val equals abs cur.val to make them all positive. Or actually, we could do this. So there we go. Now we just return res. Okay, what do we got? Oh, so this is that. Did I have an infinite loop somewhere? Looks like it. Where? Here. Okay. There we go. All right. So we have the Inorder traversal. So an Inorder traversal, I believe, is left, root, right. Okay, so let's do that. Then we have to have some kind of. So let's just make sure. So yeah, left or right. Maybe, let's see. So yeah, 1, then left. Oh, why is it saying? So it's actually saying that the Inorder should be null here, I believe. Oh no, never mind. I see. So we don't. Okay, so yeah, so it's so left is null, root. Then we have right. Then we have left. Yeah, so we take this root, we go here, we left root. Yeah, okay, perfect. So res equals this. Then we have a traversal function node. So if not node, return. We just return. Yeah. Then we do traverse. Yeah. Node dot left. Traverse node dot right. And then we output this value, so res dot append node dot val. Okay, now we just call it and return res, right? So traverse root, return res. Sure. Okay, what did we do? Let's see. Output 321, expected 132. Interesting. So we traverse. Oh, right. So Inorder is left root. There we go. Okay, and then for the pre, we're actually gonna do a little cheat, copy this code. And all these traversals are the same, you just do it the other way. So pre is left, right, root. So we can just swap those, put that here, and bam. Oh. What? Okay. Not quite. Did I do? Oh, okay, no, I screwed that up again. So actually, preorder is root, left, right. Yeah, okay, there we go. There we go. Post is left, right, root. Okay, cool. So let's go over these real quick. So this is pretty straightforward for paint, or not paint, or reverse linked list. So let's say we have these nodes, right? Let's draw real quick. 1 goes to 2, goes to 3. And this is going to be a sub-problem in a lot of like the hard and the medium linked list problems. So you're definitely going to want to know how to do this well, and maybe even like you know this and then use it as a sub-function in that, so you can make a reverse function that you're going to need to call multiple times. So you're going to have a cur here, you're going to have a previous before, and then all you're doing is you're saving the value that's to the next. So you're going to make temp this, then you're going to say this next is here, and then you just move these two up, right? So this cur goes over here, and then this previous goes over here. And the reason you need to get the temp is because we're deleting the next. So then we're doing the same thing. We say temp is over here, we delete this thing, we say cur next is previous, and then we move them up again, and so on. And so at the end, the current is going to be out of bounds, and previous is going to be here, so that's what we return previous. Okay, let's just actually do this space and time complexity as we go for these, so we don't have to go back. So for the space and time complexity, we're just going to be going through the entire list once, so it's just going to be O of n. And we're not making any new data structures, so space is O of 1. Merge two sorted lists, pretty straightforward. So we just have a pointer to, so let me draw this real quick to show this. Yeah, so we have this 1, 2, 4. Then we have 1, 3, 4. And so what we're going to do is we're first going to make this dummy node, and then we're going to have our current be here, and then we have 2 pointers here and here. And then we say which one is smaller. So for in this case, it doesn't matter. So let's say we take this top one. Then we make our current next that node. So it would point up here. And then now we point here, and we also need to delete this thing right here. So now we're pointing here. Then we say, okay, which one is smaller? It's the bottom one. So it's going to point to the bottom one. Same thing. Now our pointer moves here, and this is whatever. And so what's going to happen at the end is one of these is going to be out of bounds. So let's say this one's out of bounds, and we have some like this is not going to be exactly right, but let's say we have something here. So this one is pointing out of bounds, and this one is pointing here. So we need to finish whatever list isn't out of bounds. And so that's why we have these extra while loops, just to make sure that there's still some extra thing to process. But we don't need to compare because one of them is going to be out of bounds at that point. Okay. So the way to do palindrome linked lists, I'll just talk about it. I'm not going to code it up. Is the big O of one solution is going to be like this. You need to find the middle of these lists, whatever it is. So you need to find the middle, and there's going to be two cases, right? It's either going to be an even or an odd. So if it's an even, you need to find the middle. You need to delete this edge, and then you need to have a pointer over here. And then we need to use the reverse that we made earlier. So we need to reverse the second list. And so now the second list would look like this, right? It would look like 1, 2. And then we have another pointer over here, and then we simply just go down the lists and letter by letter, and we compare them. And if there's something not equal, then it's not a palindrome. So it's pretty straightforward. You cut at the half, and then you reverse the second one, you compare. Now the other case is if it's a odd number, right? So if it's 1, 2, 3, 4, 5, then what you're going to need to do is you're going to need to cut right here. So you can figure out if it's an odd number by doing some kind of traversal and just keeping a count, or you can have a fast and a slow pointer. And I'll talk about that in the next questions. So we delete this here. So this is going to be 1. This is going to be the pointer here. Same thing, reverse, right? So it's going to be 5, 4. And this first one's going to be 1, 2, 3. Now, technically, if it would be a palindrome, it wouldn't be 1, 2, 3. It would be like 1, 2, 3, 2, 1, right? And so it would be 1, 2, 3, and then 1, 2 when we reverse it. So then when you have this 1, 2, 3, 1, 2, you do the same thing. You compare characters. If they're not equal, then we return false. But if there's one character in one and the other one's none, that's fine. And that's what's going to happen if there's an odd number. But you have to make sure that the big part is the first list, and then this small part is the second list that we need to be reversing. Okay. So remove linked list elements. So this is pretty straightforward. This is just like that dummy thing in some previous questions. So we just make this dummy node. We go through the list. Let's say we're trying to remove 6, like 3, 6 or something. So we just go down this list and we say, okay, is it not the value we want? Okay, in that case, let's add it to the dummy, make the pointer point over here, and delete this. And we keep doing that. And then if it's something we don't want, we do the same thing, except the only thing we change is we just move to the next one, but we don't append anything. And so that's what we're doing here. If heads val, just go to the next one. And that way we traverse. Oh, actually, let's go back and do the time and space complexity for some of these. So time is going to be, we're going to be iterating through both of these lists. So it's just going to be, if L1 is the length of one and L2 is the length of the other, it's going to be L1 plus L2. We're not making anything extra. We're just making one node. So of 1 here. Palindrome, same thing. So time is O of n. We're going through the whole thing once. Reverse doesn't add anything extra. Space of 1, we're not making anything x. Same thing here. Let me just copy this actually. This might be a lot of them. Okay, remove duplicates from a sorted list. So it's pretty straightforward as well. We have this dummy node, and the only thing we're doing now is we go through the nodes and we ask, is it in our visited set? If it's in our visited set, just go to the next node. And same thing, we make this dummy node and we connect all these nodes. And if it's regardless of if it is in our visited set or if it isn't, we can just add it to the visited set. So that's how we remove duplicates. We just go down this list, we keep adding the numbers to the visited set, and we check if they're in there. And that's going to be also exact same. So for most of these linked lists, okay, so for this middle, let's show you this one with a fast and a slow pointer that is also very common. So there's a couple things, there's 2 ways you can really do this problem. So if you have these 5 nodes, there's 2 ways you can do this problem. One, you can have a cur, and you can just go down one by one by one by one, and then you can have some kind of count, right? So you have the cur sign at the head, and you say if cur isn't null, increment the counter, and then you get some length of a linked list. But actually a trick you can do, depending on where you want. So a lot of these questions, you're going to want this first one to end here, or you're going to want it to end here. And for that, you're just going to your pointers are going to start at slightly different places, I believe. So like for one of them, the fast pointer will start here. For one of them, the fast pointer will start here. So just do it in your head and figure out where it needs to start. But basically, what you're going to have is you're going to have a slow and a fast pointer, and so a slow pointer is going to move one space, and a fast pointer is going to move two. And so what did I do for this one? So they both start at the head, and then I say while fast. Okay, so you have this slow, you have this fast, and then you keep moving them until, and like I said, this case might change depending on where you want it to stop, or you can start the fast pointer ahead. So you say until, let me see here. Yeah, so in my case, I had it stop when the fast pointer doesn't have a Sorry, my mic cut out for a second. So in my case, I made it stop where the fast pointer doesn't have a next node, but you can also have it stop somewhere else. So, and if you look how that would look like if the fast stops here, how many iterations will the fast node go? Right? It'll go once, and then it'll go here again. So it'll go twice. And then the slow pointer is going to go twice as well, except it goes one node. So you can see for this odd case, the slow pointers are going to be in the middle. And now let's check the even case. And so the way you could test it is you can have an odd and even linked list with a small amount of nodes, and it'll work for the big one. So just try like 4 and 5 nodes is good. So then we have an even one. Okay, so you have a start. So how far will this go? So it'll go 1, 2, and then it'll go one more, right? Because here it does have a next node. So it'll go 3 times. So slow will go 1, 2, 3. And then you can see that's right where we want it to be. So that's how you would do that. Otherwise, you can just go through this whole linked list, have some kind of count variable, and then figure out how many times you need to go forward. So if it's like 5 and you need to go 2, then just start the head again and increment until the count is not 0. That's the other way you can do it. Linked list cycle, pretty straightforward. So the way this works is it's a slow and fast pointer again, except the trick for a linked list cycle that you're going to have to know is in order to see if there's a cycle in a linked list, so let's just show this example, right? 2, 4 nodes. And then this is over here. Whenever there's a cycle, if you have a slow and a fast pointer, they are going to run into each other at some point. Otherwise, the fast pointer is always going to stay ahead of the slow pointer and we'll just go out of bounds. So we can test this, right? So let's just do iteration by iteration. So iteration 1, slow will go here, fast will go here. So let's delete that. Iteration 2, fast will go 1, 2, so it'll go here. Slow will go here. Iteration 3, slow will go here. Fast will go, sorry, so hold on. 1, 2, okay, so our fast is actually over here, I think. Yeah, so our fast will go here. So you could see that they run into each other here. And this will always happen regardless of how long the list is. Like we could try it with a 5. It'll still do it. And no matter where it goes, right? So we can try it with this just to show you. So iteration 1, it'll go here and here. Delete these. Okay. Iteration 2, it'll go here and here. Iteration 3, it'll go here and here. And then iteration 4, slow will come here and fast will come here as well. So after a while, and it shouldn't take too long, they're going to hit each other if there's a cycle. So intersection of two linked lists, I'm not going to draw this out, but it's pretty straightforward. All I did was I take every single value in my A and I made it negative, and then I just traverse down B, and if I run into a negative value, the first negative value is where they intersect. So that's when I can save that node, and then I traverse down A again and make all those values positive again, because they said they want to retain their original structure. There are other ways to do this without changing the node, but I'm not going to go into that in this question. And then binary tree Inorder traversal, like I said, is pretty straightforward. You just have to remember which traversal is which. So preorder is root left right, Inorder is left root right, and postorder is left right root. So you just simply traverse to where you need. You just have a helper function. If the node is none return, we traverse to the left, then we do the root, then we do the right. Inorder or postorder, sorry, preorder is root left right. And we think we skipped some time and space complexities, but so this is once again O of n because we traverse to the end. It's technically O of n over 2, but that rounds to the same thing. Linked list cycle O of n as well. Intersection O of n. We're gonna intersect multiple times, but that's not gonna add. So actually, this wouldn't be O of n. This would be, we go through both lists, right? So it would be the length of A plus the length of B, technically, because if they don't intersect, we're going to go down both of them. Okay, and then this, we need to figure out what's the worst case traversal. So it's not a guaranteed balanced tree. And so these nodes, we might have to go down all the way. But either way, for time, we're going to go to every single node, so that's going to be n. But for space, worst case is going to be n, assuming we're just going down all the way and we recurse fully, right? So for trees like this, so it's like 1, this. We're going to recurse, never return until we get to the very bottom. So that's our worst case. And then preorder, same thing. Okay, so that's all for these questions, and if you like this kind of content and want me to do more of it, like and subscribe to the video, and I'll see you in the next one.